Hello everyone. In this video, we are going to see the operation of a Baugh-Wooley multiplier. In digital systems, multiplication is not always as simple as it looks, especially when we are dealing with signed binary numbers in 2's complement form. So what we have seen till now, the traditional array multipliers like the Braun array multiplier, which works only for the unsigned data. But the real world processors are handling both signed as well as the unsigned. So that's where the Baugh-Wooley multiplier comes in. What they have done over here is this clever architecture modifies the partial product generation process so that sign multiplication can be performed very much easily. We won't add any extra components over here. Just we will adjust a partial products some way, and then we will get the signed output with a proper output. So by rearranging and adjusting certain partial products, the Baugh-Wooley design keeps the regular array structures of conventional multiplier while enabling fast parallel sign multiplication. That's a key point over here. So in this video, we will explore that what a rearrangement we have to perform in the partial products, and then how the Baugh-Wooley multiplier simplifies the sign multiplication, and then step by step we'll perform for a 4-bit input multiplication, and then we'll compare it with the normal multiplication. So straight away we'll go into the operation. So if you observe over here, we have got two inputs A0, B0, A1, B1, A2, B2, A3, B3. So always in the signed number, always the MSB is going to be signed bit. The MSB is going to be signed bit. So if you observe over here in the partial products, the B0 is going to be multiplied with the A0. So B0 A0 it's correct. B0 A1 is correct. B0 A2 is correct. But here, if you observe, there is a bar. Why it is a bar? Because since the A3 bit and B3 bit, this both are signed bits. Why? Because we are performing for sign multiplication. The Baugh-Wooley multiplier can perform for signed multiplication. So now here A3 B3 bit indicates a sign bit. So that's why you can see here A3 B0 bar. Only for the sign bit alone we have an A3 B0 bar. Likewise B1 A0 it's normal. B1 A1 normal. B1 A2 normal. But here A3 is sign bit. So B1 A3 bar. And then B2 A0 normal. B2 A1, B2 A2. But since A3 is once again sign bit, B2 A3 bar. So here the B3 is once again sign bit. So when sign bit, when I'm multiplying with a normal bit, it's going to be full of bar. So A0 B3 bar, and then A1 B3 bar, and then A2 B3 bar. And then here both are sign bits. A3 is sign bit as well as B3 is also a sign bit. So the bar and bar gets cancelled up. So we have got a normal A3 and B3. So wherever I have put circle, there and all it's a bar. And then wherever I have put a normal underline, those all are normal AND operations. And then the adjustment, as I told earlier, what is adjustment we will do it over here. We will add an 1 next to the MSB of the first row partial product. That's the first rule you should remember. Okay, we will add an binary 1 next to the MSB of first row partial product. This is the rule we should remember. So we have added up here 1 over here, and then in MSB we will add another one. In MSB we will add another one. That's the second adjustment we will perform over here. So this is the basic operation. Now we will take an example and then we will perform the same operation over there. So now I will take this. So I will keep it aside. So it will be easy for us to understand. So now here this is the input which we have taken. So now we will perform a normal Baugh-Wooley multiplier. So I will make it much bigger. So it is to be easy for us to understand. Yeah. So now we will perform for the 5-bit. So here. So it's a 5-bit. So 0, I'm going to multiply with all the bits. So as usual, 0, 0, 0, 0, and then this 0 is going to multiply with a sign bit. So usually it is going to be 0, but here you can observe over here it's a A3 B0 bar. So usually what we will do 0 into 1 is going to be 0, but we will invert it. It is an 1. So wherever I put circle, it's a bar operation. And then 1. So 1 into 0, 0, 0, 1, 0. So 1 into 1 is going to be 1. But here it is going to be 0. Because why? It's a bar operation. A3, B1, bar. And then once again, 1 into 0, 0, 0, 1, 0. Once again, it's a bar operation because sign bit. And then 0 is going to multiply with all the bits. So 0, 0, 0, 0, and then 1. Why 1? It is an operation. 0 into 1 is going to be 0. But here we have got an A3, B2 bar. So since it is in 4 bit, it is in 4 bits, but we are doing for 5 bits. The same operation. The last row alone is a sign bit. So when it is sign bit, what happens over here? The sign bit into normal bit is going to be bar. So here is going to be 1 because why? Sign bit is 0, 0 into 0 normal is 0, but you will perform bar. The last row is alone bar, and then here once again bar, once again 0 into anything 0, but it's a bar. 0 into 0 anything, it's a bar, and then the last two bits. Okay, this 0 into 1, this 0 into 1. So both are sign bits. So bar gets cancelled up. So it's going to be a normal operation. It's going to be 0. And then what is the procedure? What is adjustment we have to do? The adjustment is we are going to add an 1 next to the MSB of the first row of the partial product. So I have added a 1 over here. And then other rule is we should add an 1 over in the last stage. So I will erase it and then I will make it for so now we have got all the partial products. So now we will do the normal addition. So 0, 0, 0, 0, 1, 0, 0, the output is going to be 1, and then triple 1, sum is 1, and then carry is 1. So 1, 1, 1, sum is 1, and carry is 1, 1, 1, 0, 1 carry, triple 1, sum is 1, and carry is 1, and then 1, and then 1. So this is the output. So what happens over here? This is a number of minus 12 into 6. This is a representation of the minus 12 and this is a representation of number 6. So we have got the output in the form of minus 72 in 2's complement form. So now we need to check it, right? So now what we'll do, we will take the output 1 triple 1 0 triple 1 triple 0. We will take 2's complement 0 0 0 1 triple 0 and triple 1 1's complement, and then add 1 to the LSB 2's complement 0 carry is 1 0 carry is 1 0 carry is 1. So fourth bit is 1 0 0 1, and then we have got 3 rows. So 2 power 0 2 power 1 2 2 power 3 2 power 4 2 power 5 2 power 6. So 2 power 6 64 2 power 3 is 8. It's equal to 72. So we have got output correctly for the sign multiplication. So now what's the adjustment we have done over here? It's simple one. We have added an 1 next to the MSB of the first row partial product. This is the one step we should remember over here. And then we have added a one more 1 to the last row of the MSB, next to the last row of the MSB. These are the two adjustments we have done. And then whenever the MSB bit, sign bit is multiplied with a normal bit, we have taken bar. So you can see wherever I put circle, those all are bars. So this is how we can perform an sign multiplication with the normal simple partial products. So this is more like a simple multiplication, but we can perform for both unsigned and signed numbers over here, which is very much easier compared to remaining sign multiplication operations. So through this video, we have learned how we can perform for a 4-bit Baugh-Wooley multiplier and 5-bit Baugh-Wooley multiplier. So now if you see the architectures over here, so wherever the gray cells are there, so the gray cells, you can see there is a NAND gate because it's a bar, right? So it's a NAND gate. You can observe over here. So you can see here it's a NAND gate. So it's a bar. Wherever it's a white cell is there, it's a normal multiplication. So you can see here, as I said earlier, for 4 bits, the sign bits will be there, right? So here. Here you can see that wherever the gray cell is there, these all are bar cells. These all are bar cells. Wherever white cells are there, it's a normal multiplication. Then you can ask me that where is the one we have added up. So where we'll add the one next to the MSB of the first row of the partial product, right? So now you can see here, it is in the P0, P1, P2, P3. Sorry, P0, P1, P2, P3, P4. In the P4 column, we are adding a 1. In the P4 column, we are adding a 1. So see the same block diagram. In the P4 column, we are adding a 1 over here. And then at last, we are adding a 1 over here. Why we are adding a 1? For adjustment of, to make it as a sign multiplication with remaining same partial products. With the simple partial products, we can perform a sign multiplication. That's why we are adding a 1 over here. 1 over here. Where we have to add a 1 next to the MSB of the first row of the partial product and then next to the MSB of the last row of the partial product. These things we should remember. So with this video, we have explored about a 4-bit Baugh-Wooley multiplier, and then we have seen an example of a 5-bit, and then we have seen the architecture of a Baugh-Wooley multiplier. Thank you for watching.